Thanks, Nicolai, and thanks everybody for coming back for the talk. I'll try to do as well as Jean-Nguyen did, but that was really an amazing talk. So I'm going to be talking about machine learning and in particular earthquake monitoring. And so we can think of that earthquakes as points. They're not really points, but we can treat them that way in terms of making catalogs of earthquakes. And I'm going to show some results from my group. There's much more activity, of course, but I'm going to focus on work that we've done in order to get better, more comprehensive point clouds or seismicity catalogs using the methods of machine learning. So there are many different ways in which machine learning can be used. This just lists some of them. So there's supervised machine learning, and that is where you train machine learning models using what are called labeled data sets. So for example, if you're picking P waves, examples of waveforms with the label saying this is a P wave that goes along with it. Seismology is absolutely set up for supervised machine learning because seismic network analysts have picked and quality controlled literally tens of millions of seismic wave arrival time. So most fields have more of a problem with that. For us, it's really easy and low-hanging fruit. Unsupervised machine learning are machine learning models that do some sort of clustering or some sort of pattern recognition in data that's not previously labeled. There's been much less work in seismology in this area, but I think it's an important part of the future as we try to discover new things in data that haven't been seen before. And then semi-supervised learning is a way of sort of leveraging modest-sized data sets to become larger and thus effective at deep learning tasks. So I'll give one example of that that we've developed over the last year or so. And then there are other things like transfer learning and self-supervised learning and yet other modes. So Nicolai said that this is sort of a hot trend, and I think that's true. And I think it took a while for seismology to get back into machine learning, in particular artificial neural networks. They were popular way back when I was a graduate student, before computers were capable, as capable as they are now, before machine learning models had as many layers and as much explanatory power as they do now. And so people like me were sort of resistant initially based on that previous experience. But there's no question now that in seismology, as in other fields, there's much that we can do that we couldn't do before, or that we couldn't do so well before due to the power of deep learning. I'm going the wrong direction. And so Mustafa Musavi put together a database for making this plot, and I just wanted to point to his GitHub page because he did just massive amounts of work to do that, and he's trying to recruit the community to develop that database. So go have a visit and contribute your papers or papers that you think are important to that. He would appreciate that very much. Okay, so there are different categories of how machine learning has been applied in seismology. Most of it focuses, I know you can't read most of this, but it's in the paper. Most of this is in the sort of routine processing or automating tasks like phase picking. That's what I'm going to talk about mostly. There's also great potential in exploratory data analysis and simulation and in solving inverse problems. Much less attention has been paid to those, but I think that will change in the future. Or it really is changing. So in seismology here, we now break it down into specific tasks, a little more granular, and also by the approach, whether it's supervised in blue, unsupervised in green, and so on and so forth. And many of these have earthquake monitoring, seismic monitoring in one form or another or at least they're relevant for that task. And that's what I'm going to talk about today. Keep hitting the wrong button. Okay, so here's an example of a machine learning-based earthquake catalog. This is part of the catalog that Tan et al. Developed for the 2016-2017 Amatrice, Italy earthquake sequence. Overall, we got something like 13 times as many earthquakes as were in the already quite dense catalog. We actually got close to 50% more than that, but the 900,000 earthquakes in the catalog is just the subset that we could locate accurately. The full catalog has 1.4 million earthquakes in the space of a year. That's about one every 20 seconds on average, or about as densely as we can pick them, or at least pick and associate them. Anyway, what you see is going from the standard catalog to the machine learning catalog, the detection, the magnitude of completeness drops by an order of magnitude, and our data, the point cloud that we develop suddenly becomes very dense, very information rich, and we absolutely need new approaches to extract understanding from those richer data sets. So I'm going to talk now about how those kind of catalogs have been created. One method that's proven quite effective is similarity search. So that's going from the waveforms straight to the catalog. So processing continuous waveform data. Template matching takes a known earthquake and tries to find a repeat or near repeat of it. That's one way. FAST is a set-based similarity search that sort of does the same thing but kind of approximately, and it's designed to do it in an uninformed way so you don't know the template ahead of time. You just compare, in a sense, compare everything with everything, or all times with all other times. That raises some computational issues, but those can be overcome with locality-sensitive hashing to a large extent. And then a further generalization is to use machine learning. So that's one example, and I'll show you how this can improve things. So this is yet another method developed by Rob Skumal, applied to the seismicity data from Oklahoma and Kansas. So this is in the middle of the U.S. If you know your U.S. geography, this is meaningful. If you don't, it's not. But it's sort of in the middle of the U.S. Has been over the last decade a lot of fluid injection there and a lot of human-induced seismicity from that. And what this shows is if you go from the USGS comprehensive catalog, has 11,500 events, you apply a similarity search to that same data, plus, and it's a little complicated because Skumal had 40 other stations. That's like 10% more data, but he gets 400% more earthquakes. So it dramatically improves the detection threshold. You find 4 or 5 times as many earthquakes as in the standard catalog. So that was going straight from the waveforms to the catalog. We can also go through a more classic approach shown below, or workflow, where there's pre-processing, picking individual seismic phases, associating those phases, so figuring out what discrete seismic events are giving rise to them, then locating and characterizing them. And for each of these tasks, we and others have developed machine learning models where the architecture is sort of fit for purpose given what we're trying to do, and is trained typically with these very large data sets. Okay, so if instead we apply deep learning to that same augmented data set, we go from having 11,500 earthquakes to having 264,000 earthquakes. So 23 times as many earthquakes as in the background, as in the standard catalog. And what you can also see is that all this structure, which was previously only hinted at, emerges. You see widespread conjugate faulting at the scale of hundreds of kilometers. And that was hinted at in the previous catalog, both by the seismicity and the focal mechanisms. Here you can just look and see it. So we've gone from using a sort of strict detection threshold or method of strict waveform similarity to a more general similarity, where instead we're using the fact that P waves and S waves have similar features, and we can use that to identify them. That generalization is what allows us to go from what's on the left to what's on the right. Yeah. Yeah. So that's the fault map for Oklahoma. I mean, if you took the dot product of that with the seismicity trends, it would be 0. I mean, they're almost completely unrelated. And it raises some interesting questions about, these faults are more or less optimally oriented in the stress field. Were they pre-existing over this scale? I mean, it's kind of amazing. But yeah, it has almost nothing to do with the fault map, except perhaps this fault here might act as a permeability boundary or a flow boundary. And so you can see that the seismicity is active here, it's inactive on the other side. But in terms of the actual lineations, seems to be very little relationship. Okay, so the key for doing that is picking the phases. So picking the P waves and picking the S waves. And so this is work done now 5 years ago by Wei-Chung Zhu, where he used ground motion from Northern California as input. So this is 3 components of ground motion. And he trained a machine learning model to classify each point in those time series as one of 3 things, either P waves or S waves or noise. So rather than just picking the P wave or picking the S wave, the way he set it up was to output this probability, classification probability. So it's tempting to think of these as uncertainty distributions of the arrival time of the P wave and the S wave. That's not what those are. Those are classification probabilities. And he just made up this label of having a truncated Gaussian with 0.2 of a second, both for P waves and S waves. But the important thing he did was to sort of engineer things so that the classification probability output peaked at the P wave and the S wave time that were labeled in the catalog. So he sort of tricked it into solving basically a regression problem, outputting 2 numbers, a P wave and an S wave time. Previous approaches for doing this treated it as a regression problem. Talk about that in a bit. And in a regression problem for this application, you use that 30 seconds, in this case, of input to output 2 numbers, a P wave time and an S wave time. That's not the approach he used, and for reasons I still don't fully understand it seems to work better. Okay, so here's examples of the output. Here's some nice, well-behaved seismograms. Picks the P wave and the S wave in each case. Here's some badly clipped seismograms. These seismograms are clipped due to the limitations in the telemetry system, not the seismometer, or not only the seismometer. And because it was trained on a very large data set that include many such examples, it knows how to do that, just like a seismologist would. And the same goes for very noisy data, such as shown in the bottom 2 panels. It's able to focus on the features that define the P and the S waves rather than all the long period noise that seems to be getting in the way and would for many standard approaches. So it's a very effective approach. All right, so this is this is the input. PhaseNet, the machine learning algorithm, outputs these classification probabilities and gives you, and from that we threshold this and we get to numbers. There's a different approach that Artemy Novoselov took that's similar to earlier efforts in picking P and S wave times, and that's to do it as have a feature extraction module for the seismograms, and then do a regression just to estimate the P and the S wave times. And the reason he went back to this is he wanted some way of picking or assessing the uncertainty or the confidence in the picks. And so what he did was to batch things differently, sort of sample the data, and then use something called dropout, where pieces of the neural network are omitted. This is all sort of like bootstrapping. And to do the regression, and you get slightly different outputs, and in your output you build up a probability distribution, and that is representative, hopefully, of your confidence in how good the pick is. So it's something that's closer to the uncertainty in the thing that you're interested in, which is not the classification of the wave, it's the arrival time of the wave. And I'll show you an example of the output for this at varying signal to noise levels. When the SNR is high, it does quite well. Now as the SNR is getting lower, you can see the P wave and eventually the S wave starts to hop around, and the uncertainty gets, the distribution gets broader, and the pick becomes progressively less certain. So for, yeah, Marie? These are the sort of dropout based probabilities. So they're aspects of uncertainty that they don't capture, but at least they capture some. Yeah. Okay, so this is an approach for those who are interested in the arrival time uncertainty. We all should be, to getting that. But we haven't really applied this to continuous data for any very interesting problems. So if any of you are interested in that, I'd be eager to do what I can to help. Okay, so in training these networks, one thing they need is a lot of data. So people say that deep learning is data hungry. We have a lot of parameters, weights and biases in these neural networks that have to be constrained, and you need a lot of data to do that. And we have great data in seismology, but we have, fortunately, limited numbers of very large earthquakes, so that sort of data is rare. Limited number of nuclear tests, that's also a good thing. But these are problems we're interested in. And so an approach to addressing those is to generate new, in quotes, new data. And that could be synthetic data. It could be combinations of data and combinations of data, signals with signals and signals with noise, and so on and so forth. And the idea is that by training on that larger data set, you'll have a more robust model that better generalizes to new situations. Okay, so what does augmentation do? So this is boiling it down to two dimensions where we have negative training data and positive training data. So the idea is that let's say we're looking at S waves. So the negative training data is parts of a seismogram that are not an S wave. The positive training data is parts of a seismogram that are an S wave. And so this is where the true bound, and that field extends out here. This is the true boundary between S waves and not S waves, if we could reduce it to just two features. But our learned boundary, because we have limited data, is only a crude approximation to that true boundary. And so everything up here is going to be a mistake. The model's going to say that's not an S wave when actually it is, and everything in the lower left will also be a mistake because it'll say that's an S wave when it isn't. And so with data augmentation, the idea is that by introducing more training data, you shift the learned boundary closer to the true boundary, so you make fewer mistakes of both kinds. So let me illustrate that with a couple of examples. Here's a really simple example where we train it to pick, say, a P wave arrival time. But if all the input data, when we train it, has the P wave arriving at 10 seconds into the window, the machine learning model is going to completely ignore the waveform and put it at 10 seconds because it'll get a perfect score when it does that, and it's easy to do. So if you then apply that model to this seismogram, you'll get a peak in probability. You'll get a peak in probability right here, which is in the wrong place. So what you have to do is sort of shift it around so that the model learns that the P wave arrival could be anywhere within the window. And once you do that, then with the 0 to 30 second shift, then it properly, keep pointing to the wrong one, then it properly picks the P wave at its true arrival time. So that's just a sort of a silly example. Here's a little more interesting example. So if you train your neural network to pick only one P wave and one S wave within a window, then that's all it will do, even if there are two earthquakes. And so here's an example where we have two earthquakes within the window, one here, one here. If we train the model to pick only one, then it picks the bigger one, ignores the smaller earthquake, whereas if we train it to understand there could be more than one within the window, then it's smart enough to find both of them. So this is a less trivial example. It would also be teaching the model to do exactly the wrong thing, which is to ignore previously undetected earthquakes or small earthquakes. That's what we were training this to do. Okay, so the model was trained in Northern California. Yenjo Tan applied it to the Amatrice, Italy earthquake sequence, developed a catalog with over 900,000 well-located events. Mentioned we threw out 500,000 earthquakes. The standard catalog had 82,000 or so events in it. One interesting aspect of this is that the machine learning model is able to pick just as many S waves as P waves. So that's a new thing in seismology. S waves are harder to pick because they occur they're not the first arrival. And so there's wiggles around them, but machine learning models are very good at picking them anyway. And in terms of tomography, seismic imaging, I'm not sure that anyone has really exploited this capability yet, despite the fact that it's been around for 5 years or so now. Also wanted to point out that we did not retrain the model for this study. It's the model trained in Northern California applied to Italy. Yeah. Yeah, I'll get to that in a little bit. So there's a step that, so this is just, so what you do is you go through continuous data, you make all those picks, and then you have to figure out what earthquakes they're coming from. And so that connecting the phases to the earthquakes is the key step. It's called association. And some of those phases are associated, some of them don't, some of them could be false detections, or they could be small earthquakes that aren't detected by enough stations to locate. Is that what you were asking? Yeah. Okay, we'll talk about that in a bit. Yeah. We'll talk about that in just a bit. Yeah. So that's a work in progress, and the answer is yes, but we haven't really done it yet. I'll show some examples. Okay. So Lise and Jean-Marie are responsible for monitoring Mayotte in the southern Indian Ocean. And Lise had just left Stanford when she started working on this, so naturally she applied PhaseNet to their data. First, again, not retrained, but from Northern California, and found that it did a great job of detecting particularly volcanotectonic events, even though it's an oceanic crust. And so the two of them implemented, and others, implemented PhaseNet within the earthworm workflow, called it PhaseWorm. I love that name. We put it in the title of the paper and the editor rejected it. So I'm still bitter about that. Anyway, it works really well at VT events. So it works, so the previous automated method, the three colors of green here, previous automated method missed most of the events. The PhaseWorm found as many or more events as through manual detection. It worked relatively well, but still not as well as manual detection for long period earthquakes. It was not trained on long period earthquakes, and actually the real problem is that the associator within earthworm can't use S waves to associate. It's like hard-coded. And if you do use S waves to associate, you can find lots and lots of LP events, even though it wasn't trained on them. And in a follow-up paper, Lise and company showed that there were large numbers of these LP events where the phases were detected by PhaseNet, and with a proper associator, they were able to find them and locate them. And in an interesting way, similar to what Wilding and others have found for Hawaii, the long period earthquakes, well, they're deep, but they're also offset from the volcanic edifice by a few tens of kilometers. So this shows the density of LP events. So really nice application, generalized to a new situation. Sometimes it doesn't work out of the box. So we tried working with Naoki Uchida on SNET data, which is the cabled observatory offshore Japan that was installed post-Tohoku. So the cables are shown here. That cable is buried in shallow mud, and anyway, the pics don't look, the waveforms don't look like waveforms from land-based data. So Naoki and company retrained PhaseNet to work with those data, and we're able to pick many, many more phases, get about 7 times as many earthquakes in the offshore region where SNET is compared to the standard catalog, and use that to show that there was a category of events that we think is related to porosity collapse of basalt in the subducting plate. It's at the right, it occurs above the slab, this extra seismicity, and it's at the right pressure and temperature conditions for that to be happening. And this just shows that. So you mentioned PN. I always get that question when I gave this talk. Finally, we decided to do something about it. So this is Albert Leonardo Aguilar Suarez, who by the way, asked me to, if any, he's interested in doing a postdoc at Grenoble. So if there's an availability, he asked me to look into that. He's going to graduate within a year or so. Anyway, so so regional seismic phases. So most of the machine learning models, like PhaseNet, are developed for local phases, where we're looking at direct arrivals. When you get to larger distances, like this is for an earthquake again in Northern California, because that's where I'm from, you get these phases that turn in the upper mantle, PN and SN. And for regional seismic monitoring, those are critically important phases. And regional seismic monitoring, and they have very different character. Regional seismic phases are important just because we have thin instrumentation over large parts of the Earth. So these parts of the Earth that are in green is when, by our definition, we have good local earthquake monitoring, at least temporarily. The much larger areas in pink are where we have to rely on regional phases to detect and locate earthquakes. So there's lots of interesting places, like much of Indonesia, that fall into that category. So he developed, and it was just published a week or two ago, a very large labeled data set that has extensive quality control from the stations and earthquakes, as shown in the left and the right, large numbers of PN, SN, relative to PG, and SG, many unlabeled ones, or labeled only generically P and S. And this is the distribution with distance, showing that there's we were trying to get a thicker distribution at regional distances to train, to be used to train models at these distances. So I'll just show a few examples. We use a longer receptive window, so 5 minutes instead of half a minute for picking these phases, because they're spread out over a longer distance. Because of that, we added a few extra layers to the convolutional neural network in order to have the bottleneck be about, the narrow part of the network be about the same width, so it has similar expressive power for picking phases. Anyway, here's a relatively simple example that picks P and S. Here again it picks, these would be PN and SN. They're separated by 120 seconds, so this is a regional phases, definitely. Here's an example where we have a bunch of different earthquakes, and we trained it to, and so it's able to pick multiple PN and SN phases. Here's one where there's a local earthquake and here, P and S, and a regional earthquake, P and S, and it's able to figure all that out as a seismologist would. Here's one where it can't do it. So here's PN from earthquake 1, SN from earthquake 1, but there's another earthquake that's interfering with our ability to recover this S-wave pick. So it's not going to solve all your problems, but it's an effective way to pick regional seismic phases. Yeah. Say it again, where there's... Mm-hmm. Oh no, it often finds just one. Yeah. So but yeah, they're weird things that I don't know much about regional phases, but sometimes they get blocked, and there's a lot yet to explore about regional phase propagation. But it's perfectly happy to pick one and not the other. Okay, this is just one example for an outer rise event off North Chile. So it's out here. Only regional phases are available, and we applied. He calls it Skynet. The editor's going to make us change that too, I'm convinced. Skynet for P and for S versus PhaseNet for P and for S. PhaseNet's not trained for this sort of data. It actually makes some picks, but it gets confused and doesn't make as many picks as Skynet does. So another important example is OBS data. So this is work that she et al. It's about to come out, I think, working on a year of OBS data from Tonga, Fiji. So it's a really nice and dense seismic network centered on the subduction zone with just some island stations, but a limited number of earthquakes for which we have PNS labels. So this is where we use semi-supervised learning to leverage those labels to get more labels that can then be used to retrain the model. So it's a recursive loop where we use the output, effectively the output of PhaseNet to retrain PhaseNet. Recursion is potentially unstable, right? If it's getting bad picks, then it'll learn to do bad picks and it'll just go bad in a hurry. But there's an intermediate step that effectively does quality control, and this is that phase association we were talking about. So phase association is figuring out which waves belong to which earthquakes, and as long as you have some sort of sanity check like that, then you can, with some care, use a semi-supervised approach such as this. And so this is the result. So these OBS deployments are expensive to carry out, lots of ship time, and so on and so forth. So we're able to squeeze an order of magnitude more earthquakes out of the same data using this recursive deep learning approach. You can see earthquakes at all depth with a possible gap here at shallow depths, but a sort of continuous sheet of seismicity within the Benioff zone. Doesn't show here, but in cross-section you can easily see the double seismic zone. This is just from a year's worth of data. So the seismicity is not completely stationary, and the new events we're detecting are the small events, but it's almost like the OBS deployment was for 10 years rather than 1 year, because we get 10 times as much, more than 10 times as much information out of it. Okay, so the key to making that stable is phase association. This is connecting the waves with the earthquakes. That's difficult for all these reasons shown here. We don't know a priori how many earthquakes there are. The events can have overlapping waveforms, as we've seen. Small earthquakes are recorded on just a few stations, whereas large earthquakes are recorded across the network. the network, there are dropouts, the geometry is irregular, it changes with time. There's background noise. We will, if we try to detect small earthquakes, and by making the detection threshold low, we will get more false picks, so we have to deal with that. And then each time or each step in the workflow, we threshold information and potentially lose it. So running a little bit slow here. I'll just say that we developed two methods for association. One uses a soft clustering method, a Gaussian mixture model. The one we're working more on now uses a graph neural network that's designed to work on irregular geometries where convolution wouldn't make sense. So Ian McBrearty is the student who's developing that. The idea is we have a station graph, a potential source location graph. We take their outer product, and we train it on pick data, so where we put lots of false picks in, and the output is a heat map, which is the source prediction in space, which is shown here. There's a third dimension in depth, and also in time. The other output is which picks are associated and which picks are not. And applying it to Northern California, we see that it's able to detect small earthquakes on a small part of the network, larger earthquakes that are recorded across the network. And we get smaller magnitude events, aftershocks of an earthquake on the creeping section, and we can look at a record section of those and convince ourselves that these are really legitimate detections. Yeah. These are associated with a 1D velocity. No, it's actually a 3D model, but it might as well be a 1D model because it's pretty weak heterogeneity. But the way he set it up, he actually trained it on synthetic data, and for the forward problem, he uses a fast marching method in 3D structure. So if you have the 3D structure that you trust, then it's easy to use that. Okay, so comparing the two methods, the one I didn't describe, the soft clustering method, and the GNN-based method on the very dense recordings, temporally dense recordings of the earthquake in Turkey, what we found is that the graph neural network-based model does a much better job, at least in this instance, of associating phases it should and not associating phases it shouldn't. And the way you can tell is these gray background events are either artifacts or they're events that are mislocated because the associations are inaccurate. And we can assess that sensitivity by just adding false picks to the data and reassociating. So when we do that, say going from 1 to 5 to 10% false picks, we find that the soft clustering based model finds a lot of new events which presumably aren't real, whereas the graph neural network based event is resistant to that. It doesn't find those extra events, which it shouldn't. Okay, so we have this point cloud. That's Yangtze Park. He assures me that's just water he's drinking. That was the picture he chose to send me. Anyway, this is the fault map that we looked at earlier. And our bias is to think of earthquakes as happening due to slip on planar faults or piecewise planar faults. And these are mostly strike slip faults and close to vertical. And so you can sort of, you could draw in a fault map by hand for much of these structures if you wanted to. Now, so we thought, we'll just cluster them. But all these clustering methods don't do the right thing. Or you look at the output and it's not what you would do. It's not even close to what you would do. So we tried all these different methods, and I don't know anything about clustering, so it was very much a learning process. But what we settled on, and if you have better ideas, I'd love to hear them, was kernel density ridge regression method that started with the points in the point cloud, developed their density, found ridges within that, defined normal vectors, and then used that to develop the clusters and segments and assign basically points to clusters. And that gave us this set. of 430 clusters within that data set that express this sort of conjugate character to the faulting. And I wanted to mention that that conjugate character is seen, this is the Pawnee earthquake and its aftershocks. It's seen at the largest scales. This is 3 kilometers there, so this is like 5, 8 kilometers. But if you can see, even at smaller scales, in fact, at every scale you can resolve, we see that same pattern. So we can use this clustering to develop spatial dimensions to these clusters. We do that using a minimum bounding box. Then we can use a simple constant stress drop crack model to relate that to an equivalent magnitude. That is, for clusters of that length, how big of an earthquake could they support if that whole cluster ruptured? Another way, and our idea in doing this is we want to look to see if the larger events in Oklahoma, Kansas occurred on faults that were illuminated by smaller earthquakes before the larger earthquake occurred. So we do that if the length equivalent magnitude in this case is 5.3, and it gets that big before we see the 4.2, then we say it was pre-illuminated and can assign some higher than background, higher than Poisson probability to it. Anyway, we did that for the entire catalog, and if you interpret things, which is shown here for each of 60 clusters, if you interpret that in terms of a probability, then the forecast probability in an absolute sense is low. That is, if you're forecasting based on the size of an illuminated structure, there's only something like a 5% chance of having an earthquake larger than magnitude 4 on it. But this is something like 7 times the background Poisson probability in the USGS hazard map. So the probability is low, the probability gain is substantial, and so presumably it's useful. And I'm certain that it'll be possible to do something more intelligent than that sort of survey. So I'll just leave these conclusions up here and take any other questions you might have. Thanks.